Hello and welcome to another video for Calculus 1. In this video, we are going to briefly discuss about mean value theorem. So the first theorem that we are going to look at is Rolle's theorem. So this theorem states that let f be a continuous function on the closed interval ab. So there are a few conditions that we need to remember or that we need to pay attention here. So f must be continuous on the closed interval ab. So that's the first condition. And differentiable, so continuous means there's no break. We can draw the graph without lifting our pencil from the paper. Okay, so it's a smooth, continuous graph. There's no break. And then differentiable on the open interval. So that's the second condition. So it should be differentiable in the open interval. So continuous in the closed interval. That means the endpoints are included. But differentiable on the open interval AB. That means the endpoints are not included when we check the derivative. And the third condition is if f of a equals f of b, which means the y value at a, or the value of the function at a, equals the value of the function at b, or the height of the function at a equals the height of the function at b. Now, if we have all these three conditions satisfied, then there exists at least one point c in the open interval ab, means there must be an x value in between a and b such that the derivative at that value or that point C equals 0. So let me draw a graph just to give you an idea of what we are talking about. So let's say I have a graph here. So this x-axis, y-axis. Let's say this is point B. So let's say this is A, this is B. So the graph is continuous on closed interval AB. So it's a smooth, there's no break. And differentiable, again, it's a smooth graph, there is no sharp turning point. So we can find derivative at every point in that interval AB. Okay, so that means it's differentiable. And then we have f of a. So this is f of a. It's the y value at a, f of a. And then if you look over here, I have drawn that at the same height. So f of b is equal to f of a. The y value is equal. So if we have that condition, then it says that we can guarantee that there must be at least one point in between these two numbers. Okay, there must be at least one x value here, which is c, such that the derivative at c is 0. Or we can say it's a couple of things from here. When the derivative equals 0, that means the slope of the tangent line is 0, or there must be a tangent line which is horizontal. Okay, so now you can clearly see that from the graph. At this point, there's a horizontal tangent line, or there is a point where the derivative is 0. Similarly, here the tangent line must be horizontal. Here the tangent line must be horizontal. So there are a couple of points. We have 3 points in this graph. You could just have 1 point, or you could have more than 1 point. But if those three conditions are met, then there must be at least 1 point in between a and b such that the derivative is 0, or we have a horizontal tangent line. So that's all this Rolle's theorem says. So remember that when you're applying this theorem, first you need to check the condition. Are those three conditions satisfied or not? If they are not satisfied, we cannot apply the Rolle's theorem, or we cannot say the derivative must be 0 at a point in between A and B. That could be a point, but there is no guarantee we can say that without meeting those three conditions. Okay, so let's look at an example here. So again, the first condition that we are going to check is the function continuous on the closed interval. So we are given this closed interval 3, 7. So now this is a quadratic function, or any polynomial function is continuous on the domain. So this is obviously f of x is continuous on 3, 7. Okay. The second condition is this function differentiable? Again, it's a quadratic function. You can draw this one. This is a parabola facing up. There's no any sharp turning point. So we can find the slope at every point on that graph. Okay, so that means it is differentiable. So f of x is differentiable on open interval 3, 7. And the third condition that we need to check is f of a equals f of b. So here a is 3 and b is 7. So we need to find f of 3, which is basically you are going to plug that number into our function. So 3 squared minus 10 times 3 plus 16, and that gives us, you can calculate that, which is -5. Similarly, let's find f of b, or f of 7. Again, 7 squared minus 10 times 7 plus 16. Again, this gives us -5. So here we have f of a equals f of b. So all three conditions are made. So we can say f of x meets all three, or we can just add all conditions of Rolle's theorem. Now, which means we can apply Rolle's theorem to find a point in between 3 and 7 that has a derivative of 0. Okay, so therefore, there exists a number C in, that E means C is in the open interval 3, 7, such that f prime at C must be 0. So basically what we need to do now is, since it satisfies all the condition of Rolle's theorem, we are going to find the derivative, and we set it equal to 0 to find that point C. Okay, so the derivative of that function, you can easily differentiate that, which is 2x minus 10. So if you write f prime of C means, so f prime of C is, we just replace x with C, so that is f prime of C must be 0. Okay, or 2c minus 10 equals 0 implies 2c equals, if you add 10 on both sides, it's 10 on right hand side, so divide by 2, so you get c equals 5. So we know that 5 is in the interval 3, 7. So first we checked all the three conditions of Rolle's theorem. The given function satisfies that, so that means we can apply Rolle's theorem to get that point C where the derivative is 0, and we got that point C, which is 5, and it is in that given interval 3, 7. So now let's look at another theorem. So Rolle's theorem is a special case of mean value theorem, where we have an additional condition. So mean value theorem is more like a general theorem here. Okay, so this one says, so the first two conditions are same. So let f be a continuous function on the closed interval ab, and then differentiable on the open interval ab. Then there exists at least one. So this one does not have that condition f of a equals f of b, okay, because this is a little bit different. And there exists at least one point C in AB such that, so it has this condition here, such that f of b minus f of a over b minus a equals f prime of c. So let me go ahead and draw a graph here. Okay, let's say we have a function. Let's say this is a, this is b. Now let's see, what does this mean, f of b minus f of a? So if you do, so this is a, that means this point here is a comma f of a, right? If this is b, then that point right here is b comma f of b. F of a and f of b are the y value, corresponding y value for a and b, right? So now when we do f of b minus f of a, over b minus a. We are finding the average rate of change on this line from between point A and B in that line. Okay, or in another word, we can say this is the slope of the second line. Remember what we did at the beginning. So that's the slope of the second line that goes through A and B. So there's this slope of that line that I just drew. Okay. Now A prime C. So it says the theorem says there must be at least one point, okay, where the derivative is equal to this slope, or the slope of the tangent line at that point must be equal to this slope, which basically means we can see here it looks like there is a tangent line here which slope is same as the second line. Again, there is another point right here where the slope is similar to, same as that given second line. So we have 2 points here. So this is, let's say, C sub 1 and this is C sub 2. Okay, so this says that if the function is continuous and differentiable on a closed interval AV, then we must have at least one point in between A and B such that the slope of the tangent line at that point is equal to the slope of the second line going through A and B. Okay, so that's all this one says. So in this case, we have to check two conditions. The first one is the function is continuous on the closed interval AB, and the second condition is the function is differentiable on the open interval AB. So those are the two conditions that we are going to check. Okay. Now let's look at this example here. So this one says for this given problem, let's check whether we can apply the mean value theorem or not. So I'm going to write MVT for mean value theorem. So we are going to check two conditions. The first one is the function continuous on closed interval AB. And the second condition is if f of x differentiable on open interval AB. So if you have it depends on the function. If it's a polynomial function, you don't have to check anything. It's always continuous, right? If it's an exponential function, that's always continuous. If it's a rational function, logarithmic function, that's where you have to check, okay, whether it's continuous or not. This is a rational function. So the easy way to check this one is find a point where the function is not continuous. So basically for a rational function, you need to find x value that makes this denominator 0. Okay, so basically take 4x plus 8 and set it equal to 0. Then you get 4x equals negative 8, or if you divide by 4, you get x equals negative 2. So what does this say? This says that at x equals negative 2, the denominator of the function is 0, which means the function is not defined, or it has a vertical tangent line, vertical asymptote at x equals negative 2. So this function is not continuous at x equals negative 2. Okay. Now, the second thing that you check is, okay, we know that this function is not continuous at x equals negative 2. So does that mean that point is in our interval here, and that's what you need to check next? Yes, x equals negative 2 is in that interval. That means the given function is not continuous on the interval negative 3, negative 1, because it's not continuous at x equals negative 2. So what I'm going to say here is f of x is not continuous at x equals negative 2, which is same as saying f of x is not continuous on the given closed interval, which means this function does not satisfy this first condition of mean value theorem, which basically means we cannot apply the mean value theorem. So this function does not satisfy the conditions of mean value theorem. So we cannot apply it. So that's where we stop for this one. Okay. Now let's look at this one. So this one, again, do the same thing. 3x equals, because this is also a rational function. So this function is not continuous if the denominator equals 0, right, in this case. If there's a square root, then the function is not continuous where the square root becomes negative. Okay, you know this from algebra. But here x equals 0. That means the function is not continuous at x equals 0. And the second thing that you need to check is that 0 in our interval. No, the 0 is not in the interval. That means the function is continuous on the given interval. It's not continuous at 0, but 0 is not in the given interval. So the function is still continuous on the given interval, okay? So the only point where the function is not continuous is x equals 0, but that point is not in our interval, so we don't have to worry about that. So, which means the first condition, f of x, is continuous on that closed interval. So the second condition is a differentiable again. The rational function is always smooth and curved except where it has a vertical tangent. The vertical tangent occurs here at x equals 0, but that's not in our interval. So again, f of x is differentiable at differentiable on the open interval 1, 4. So it satisfies both conditions. That means we can apply the mean value condition. So mean value theorem. So this satisfies mean value theorem. Okay, the conditions of mean value theorem. So if so, then we need to apply mean value theorem. So you know that mean value theorem, the condition for mean value theorem is f of b minus f of a over b minus a equals f prime of c. So we need a couple of things. We need to find f of b, we need to find f of a, we need to find the derivative. Okay, so let's go ahead and find f of b means f of 4. Let me use a different color here. So f of 4 equals, so you can plug it in here. So 4 squared 16 minus 9 is 7 over 3 times 4 is 12. Okay, so f of 4 is, you can just plug that in here, that function. So you get 7 over 12. Similarly, you can find f of 1. So plug it in. When you plug in 1, you get 1 squared minus 9 over 3 times 1, which is negative 8 over 3. So that is f of b and f of a. b minus a is 4 minus 1, which is 3. Now let's go ahead and find the derivative of this function. Okay, so f prime of x equals, now the derivative, we have to use the quotient rule. So if you remember quotient rule, that is denominator times derivative of numerator minus numerator times derivative of denominator divided by denominator squared. Okay, so your denominator is 3x times derivative of numerator is just 2x, then minus numerator is x squared minus 9 times derivative of denominator is 3 divided by 3x squared. Or if you distribute that, you get 3, that's not correct. It is 6x squared minus 3x squared plus 27. So be careful here when you distribute that. So you get negative 27 and there is a negative sign here. That makes it positive 27. And then you get 9x squared. So you can simplify this. So 6x squared minus 3x squared is 3x squared plus 27 over 9x squared. Again, you can factor out 3x squared plus 27 over 9x squared, and then you can cancel out this 3 and goes 3 times here. So we have x squared plus 27 over 3x squared as our derivative. Now, if we apply the condition, okay, so our condition is f of b minus f of a. So we can now write that by mean value theorem, f of b means f of 4, right? So which is 7 over 12 minus f of a means negative 8 over 3. So it's negative, so that becomes positive or plus 8 over 3 divided by b minus a is 3. That equals, So our derivative is x squared plus 27 over 3x squared. So f prime of c means we just replace x with c. So c squared plus 27 over 3c squared. Now go ahead and do the denominator, sorry, the fraction on the left hand side. So if you simplify that fraction, you get 39 over 36 equals c squared plus, why did I write 27? I made a mistake here. So this should be 9. This should be 9. And then this one here, it should be c squared plus 9. Okay. So c squared plus 9 over 3c squared. Now we can do cross multiplication here. Okay, so if you do that, so 39 times 3 is 117. C squared equals 36 c squared plus 9 times 36 is 324. So subtract 36 on both sides to put that c squared together. So if we subtract 36 c squared on both sides, so we get 81 c squared equals 324 divided by 81 divided by 81. So that gives us c squared equals, so 324 divided by 81 is 4. And then if you take the square root, so c is positive or negative 2. But now, one thing that we need to remember, our interval is 1 to 4, so we cannot take negative 2. So negative 2 is not the value for our function, for that function. So c equals 2 is the number or the point. So basically this says that if we take this function in the closed interval 1 to 4, the average rate of change, or the slope of the second line going through 1 and 4, is equal to the slope of the tangent line at x equals 2, okay, or c equals 2. So it's so that's the value of the c. So that's all in this video. I'll see you again in the next video.